Hello, everyone. Welcome to the fourth and final press conference of the 50th Division for Planetary Sciences meeting here in Knoxville. I'm Shantanu Naidu. I'm the DPS press officer. Also with us is Rick Feinberg, who's the American Astronomical Society press officer, and Kerry Hensley, who's the AAS media fellow. Today's topic for the press conference is the exploration of asteroid Ryugu by Hayabusa2. And we have 6 very exciting speakers. First, we'll have Masaki Fujimoto from the Institute of Space and Astronautical Science, the Japanese Aerospace Exploration Agency, who'll talk about Hayabusa2's operations and observations of Ryugu and initial operation of the Minerva 2-1 rovers. Next, we'll have Ralf Jaumann from the German Aerospace Center, who'll talk about the initial operation of the MASCOT after its deployment. After that, we have 3 speakers, Tatsumi from the University of Tokyo, and Lucille and Deborah Domingue from Planetary Science Institute. They'll be talking about Ryugu's surface seen from Hayabusa2's remote sensing observations. And last but not least, we have Hikaru Yabuta from Hiroshima University, who'll talk about landing site selection to provide key scientific and engineering findings from proximal operations and material sampling. Before we begin, can I please request everyone to turn off your cell phones for the duration of the press conference? And I'll have Masaki Fujimoto take over.
Okay. Hello, everybody. Let me try to tell you what we have been through to come up to the stage we are now. So Hayabusa2 is an element in a small exploration program, a small body exploration program. It's about understanding how the water has been brought to the planet to make it, to our planet to make it habitable. So Hayabusa2 spacecraft look like this, and I'll be concentrating on these several instruments that really function perfectly to make us standing here celebrating the success so far. Hayabusa2 was launched about 3.5 years ago, and then it made a Earth swing by perfectly, and also the ion engine worked perfectly, so that at the early June this year, it brought the spacecraft close to the target asteroid Ryugu, and then that's when ion engine was stopped operating, and we started to do the optical navigation. This optical navigation made the spacecraft to come to its home position like this, which is 20 kilometers above the surface of asteroid, from which we can do the reconnaissance operations to get to know more about the nature of the asteroid. Actually, I have to tell you that this first close-up look at the asteroid kind of shocked us, but I'll come back to that issue. But even we are shocked by this first image we took from the home position, we kept on doing a job, like constructing the shape model, and also making the gravity field measurements. And these operations worked perfectly, but that doesn't make the surface condition of our target asteroids easier. Actually, this image shows the distribution of the boulders on the surface of the asteroid. And you can clearly see that big boulders are distributed uniformly on the surface, but yet Hayabusa2 is a sample return mission, which means that we have to touch down on the surface and get some samples. And this is really the moment we realize that this is not going to be an easy mission. But still, we stay determined, of course, and we have to progress. We have to make a progress in the mission. So that's why we made a landing site selection rather early in the phase of the mission, because otherwise we cannot make a progress in the mission. So the left-hand side shows the landing site selected for the main spacecraft where the sampling will be made. And then onboard Hayabusa2, we had 2 small landers, well actually 3, but 2 of them has been operated already, so I'm just focusing on those 2. 2 small landers in the middle is the German-French lander, and then on the right-hand side is the Japanese small landers. Then the landing site for these landers has been selected at the same time. So what's really good about having these small landers is that we got there, we got to the home position, we made a close-up images of the target asteroid to realize that the surface is not friendly to the mission. And in such a situation, any information about the nature of the asteroid, any information about the surface condition really helps. So in addition to the remote sensing operations, we have small landers that will go onto the surface and tell us the ground truth of what the surface looks like. So that's really good, and we really did perform the deployment of the Japanese small lander in mid-September. So red arrow shows the target landing site, and then so we went down, and then deployed the spacecraft from this altitude of 64 meters above the surface. And this image was taken upon the deployment of the lander. And then when the lander got onto the surface, it operated perfectly. So these are the images taken from the surface, on the surface of the asteroid. And you can clearly see that well, taking an image doesn't solve the problem, of course. Having a lander on the surface doesn't remove all those borders, but still, for the engineers, it's really good to know the ground truth. It's really good to know what the surface is like. And of course, there is some science we are obtaining from these images as well. And I'll leave that to the scientists sitting here. But anyway, information like this and like this is really helping us to fine-tune the touchdown operation scenario that we are constructing right now. And of course, it's not only this Japanese small lander, but we also had the German-French lander by the name MASCOT being deployed in early October. And this is the image taken upon the deployment of MASCOT. And Ralf will tell you how perfectly this lander worked on the surface. And I have some more updates about the most recent development, but I'll come back to that issue in the very last leg of this presentation session. And now I'll leave the floor to Ralf. So how do I? Press the reset. Okay.
Okay, thank you for having the chance to tell a little interesting story. At least for us, it was very interesting. And first, let me thank for Hayabusa, because deployment with Hayabusa was great. It was absolutely perfect. They kicked us out 50 meters above the surface. We needed about 6 minutes to the surface, and it was a very interesting travel of this small thing. And the small thing is MASCOT. That means Mobile Asteroid Surface Scout, and that's a short summary what MASCOT is. MASCOT was designed for two reasons. One is a technical one. So Hayabusa told us they need a lander, but it should not exceed 10 kilograms, and it should be mobile. And as you have seen, we have a weight which we can move, and so we can hop across the surface. We have 4 instruments: the camera, a spectrometer, a radiometer, and a magnetometer. So that's not too much, but you can do a lot with this. And the major goal was to really get the surface ground truth and information about the surface in order to connect between the orbiter data and the lander and the sample data. Okay, it's a cooperation between Germany and France and, of course, Japan and JAXA. Okay, when we get released from the height of about 50 meters, and you can see here the shadow of Hayabusa, and the track we could reconstruct. So what you see is the blue ones, which is the surface. The yellow ones is the descent, the 6 minutes of descent. It's going down. And the blue one for this part is it's a little bit better resolution, is projected to the surface. And we had in any taken ONC image, that orbiter image, we could identify MASCOT. So we really could reconstruct what happened. And you see at the end of this, I'm not sure whether I can get there, no. At the end of the yellow line, which is the fly line, there's a rock. And we crashed at this rock. And then we has been pushed back, and then we follow this slightly curved blue line to the first position. And we even could really identify this in the image where you really can see MASCOT. And MASCOT has at least one bright side and a number of dark sides. So you see it was tumbling to the surface. We'll come to this a little bit later. And then at the first position, we had the first problem because MASCOT was not lying in the correct position. It was upside down. So we have looked into the sky. All instruments have looked into the sky. And that basically makes the first decision. We had been on the surface. Everybody was fixed for an automated operations. And then we have to decide to really interact and upright, or at least we decided to make a move of MASCOT, which we already did, but it was not worthless because when we were upside down, we had Jupiter in our side of view. Okay, so during the descent, MASCOT takes a number of images, and that was the image number 2. What you can see here on the right side is the MASCOT image, and the next one was where we really look to southwestern horizon, and you really can see the same as we already talked about. We have a lot of rocks, and the next image was looking back on our track. So we really have seen what ONC has seen from the orbit. We also could identify on the surface, and that helps a lot in order to identify images in the orbiter images and the MASCOT images, and that's very important because that's our only chance in order to get the sizes of the surface features. Okay, and then we get to further rocks. So the upper right is the rock we crashed on, and if you look at, so basically you don't see anything of the crash at this rock, so that basically means the rock was not too hard. I will come to this later. And we also have 2 different instruments which were able to report what happened after deployment, and one is the radiometer, and the radiometer has about 6 channels, and the 6 channels get temperatures, and with the temperatures you really can see what MASCOT did, looking into the sun, looking into the dark, looking into the sun, and that was the first. We have a time resolution of about 7 seconds, so we really get every 7 seconds with the temperature sensors what's going on. And what we have here is after release, we have some kind of tumbling, and then we have the first surface contact, and after the first surface contact, you really see there's a lot going on with the detector. So we have been hopping across the surface. The first estimate about this was, it was some kind of a hopping of about a meter high. And then we also were tumbling, and we really get different sensors with different directions from the radiometer. And after this, we had a stop in the fast rotation, which was the descent, and then we really see the rotation on the surface, and then we got to the first position, and you see the up and down of the sensor detectors stopped, and we are laying on the surface. We could really identify the time in doing this. Then we made an upright, and then we rested in the different position, and you see we got a lot of light on the detectors on the subsurface, or on the downside of MASCOT. Okay, the next are the magnetometer, and the magnetometer also is able to really identify what's happened. So the first what you see is the up and down of the three magnetic directions clearly show that we are in the Hayabusa, because we measure the magnetic field of Hayabusa. And once we were developed, then you really don't see anything. What we could estimate from this information was that our deployment velocity, that has the kick out of MASCOT, was about 4 centimeters per second. That's very close to what we got for what we had expected. It was about 5 centimeters per second. So means that the deployment mechanism worked quite well. Okay, the next what we got was this signal, and that clearly shows that the magnetometer so far hasn't seen any field, but it has seen what happens on MASCOT. And what you can see here is the small peaks, or the small changes are the operations of the board computer, and the large ones are when the camera turned on, takes picture, and takes a lot of power. And then there's another thing, when we really clean this up, then we really see there's a drop down. And this drop down was exactly after 6 minutes. And this drop down, which we can see here, is when we crashed at the rock. And that gives us a chance from the magnetometer to really look into the data, and I will take a little bit more tomorrow, because the magnetometer is fixed on, it's not a boom, it's fixed in the instrument, so that basically means it sees deformation. And so that gives some kind of information about the stiffness of the rocks. Okay. Nevertheless, the measurement of, let's say, the magnetic field so far is very low. So we have less than 20 nanotesla. So basically means that's less, or mostly equal what we measured on Chirumo Gerasimenko. So means at least there is no real magnetic field with Ryugu. Basically means Ryugu never have seen some kind of a magnetic environment. Okay, and then that's one of the last images of the descent, and that's was the first we were really excited about, because if you look at the rocks with these images, you see two different types of rocks. There are rocks in the foreground which are really flat and bright, relatively bright, because Ryugu is dark at all. And the second part is, if you look a little bit into the middle part of the image, to see some kind of grumbled rocks. And they are dark. So from the first estimate, we know that there are two different rock types on the surface of Ryugu. Okay, we have put this together in a short timeline, and I have it here. I can distribute it. You also can find this information and the images on the DLR website. So basically go to www.dlr.de, and finally look into MASCOT, and then you get all the released images which I already showed here. Okay, thank you. And then I give to help to solve the problem.
Hello, it's a great honor to be here to show our accomplishment from remote sensing observation. So my name is Tatsumi from the University of Tokyo, and our team member is also Lucille and Deborah Domingue. They are talking different topic. So I'm gonna show some recent results. So let me introduce about our instrument, which is called ONC, Optical Navigation Camera, which named navigation camera, but it is also used for scientific observation. And we have 3 cameras. Two are wide-angle cameras, W1 and W2, and one is telescopic camera on CT. And on CT has 7 different bandpass filters ranging from 0.4 through 0.95 micron. So we have more result for spectral analysis in poster and oral sessions, so please take a look. And here I would like to show is the sequence of observations. We started from far away, like to 20 kilometers in approach, and we are getting closer to closer, and we could have many pictures which have higher and higher spatial resolutions. And we have done the touchdown rehearsal 3 today. And we hopefully going to touchdown in 2019. So this is very brand new movie from touchdown rehearsal on 14th and 15th October. So here you can see the shadow of spacecraft. It's amazing, and it's going down like this. And minimum altitude was 23 and going up. So actually yesterday's operation, we went down to 12 meters, so we hopefully obtain more higher resolution images. So during this touchdown rehearsal, we obtained the highest resolution asteroid surface image, which has 5 millimeters per pixel. And you can easily resolve centimeter scaled boulders, pebbles, and we can see some difference in reflectance of boulders. And now we go to the science field, and it is maybe very good opportunity to compare Ryugu and Bennu. Bennu is now approaching, OSIRIS-REx is now approaching to Bennu. So now we want to compare those two objects. Both are the upper group near Earth asteroids, and both probably came from the inner asteroid main belt. And it turns out both are top-shaped. And in terms of albedo, they are also quite similar. However, in terms of spectral type, they have a little different spectra. Like Ryugu has a more flatter spectral shape, while Bennu has a more bluer spectral shape. So in terms of color, Ryugu is like this homogeneous color. But if we take a look at the very detailed spectroscopic analysis, then we could find local color variations over Ryugu. And if we take a look at this boulder, this is the largest boulder on the Ryugu, so which is called Otohime, and we made a false color images for Ryugu and Bennu based on spectral photometry. We put different filter to different color channels. And Otohime turns out has very similar spectra to Bennu, so which may be suggesting some relationship between this Otohime and Bennu. So we are very look forward to seeing the results from OSIRIS-REx. So my talk is over. I want to pass the mic to Lucille.
So hello, I'm a research scientist at the Planetary Science Institute. I'm a Hayabusa2 participating scientist funded by NASA, and I'm a co-I on the ONC camera. So I'm helping process the images to create mosaics and topographic models for the potential candidate or the candidate landing sites. In this presentation, I'm going to talk about terrain models I've built using images from the Minerva operation, so during the descent of Hayabusa2 to release the Minerva landers. I used, for each site I'm going to show, I used 7 images from different filters to build elevation models. So one site, the first site, actually includes a potential sampling site that was called L07A, and the other sites you can show the average roughness of the asteroid Ryugu and how full of boulders it is. So this is how we can assess the safety of the landing sites by having topographic models. And we can see that it has lots of boulders and rocks scattered around and a general lack of smooth areas. So in this map, you can locate the 3 potential landing sites. So the N6 here is for the Minerva landers, and the MA9 was for MASCOT. So L08 was the best potential landing sites. And the images I have covered the backup site, L07, and then an area that is more left of it. So if we zoom in, so site 1, this one is about the width of American football field, and then the second 2 other ones are a little smaller and cannot represent the average surface of Ryugu. So L07A here is next to this big bright boulder, and it's located in the middle of the site 1. So for site 1, the altitude of the spacecraft was about 470 meters. And this is the image mosaic of the site using 7 filters. And this big boulder here is about 5 meters in this direction. And so we built elevation models, and I did some videos so you can see, as if you were on the surface, how it looks like. So the bright boulder is on the edge, and in the middle you can find the backup landing site. And you can see that it's pretty much boulders everywhere, and not much areas that are smooth. Let's see, and then I have another one. So this is from the top, so it's another perspective. And we can see that some boulders have different brightness a bit. I mean, it's pretty homogeneous, but some boulders are brighter a little bit, and this needs to be investigated with the color data. So the second site was images that were acquired at 230 meters, and it's not a potential landing site, so it's a bit more many boulders, on this site. I'll show this video from an angle of 30 degrees point of view, and so you can see that some of the blocks in the middle are more than about several meters high. And then from the top. So these models help us, characterize the surface and see where we could potentially sample. Obviously, this site is not very good because it's scattered with big blocks. And then the last site Site 3 that was observed closer to the surface at 150 meters. And this is also not a very good site for landing because you can see that all the blocks in the middle. So I show that one. And again, we can see some boulders appear brighter. And then the last one from the top. So this is probably the worst site. Very big blocks, couple of meters high. So it could be dangerous for Hayabusa2. And that's pretty much it for me. So I'm going to leave it to Debra.
See if that comes up. So I'm Deborah Lemang from the Planetary Science Institute. I'm also one of the participating scientists who's had the honor and privilege to work on this very amazing mission. And as you can probably tell, the big story here is the boulders, the very rocky surface, and the challenges to sample such a surface. So what I show here are a series of photographs that show or images, pardon me, that show higher and higher spatial resolution. As one of the surprises for us is as we came into our approach and establish our home position, which is the image on the far left, is that this was a very rocky surface, and the boulders are strewn all over. They come in various sizes and shapes. Some look like outcrops. So the big question for us was, is this going to be the texture as we get closer and we see the surface at higher and higher resolution? And you can see from 70 meters altitude, the image with the shadow of the spacecraft, that yes, the surface is strewn with boulders. As you get even closer you've seen some of these images already, at 64 meters altitude, you see the big block in the lower left-hand corner. It's casting a shadow. This is a huge boulder. You see pebbles, rocks, things on the size of centimeters. Even from the image taken from the rover, you see a very, very rocky surface. And there are posters this afternoon and talks tomorrow morning that delve into the characteristics of the boulders, the distribution, in addition to the additional geology of the surface that I would highly recommend. But for us, the question is, where are we going to go get our sample? And the camera is not the only instrument we have to look at the surface or to characterize the surface. What you see here is an image provided by the thermal infrared imager. We were lucky enough that Okada-san provided this image for our presentation today. And it shows the thermal properties across the surface. It has been mapped at high spatial resolution. This is one of the lower spatial resolution maps. But from this data, we can determine something about the grain size of the surface. And we can compare and contrast with that object we know oh so well, the moon. And what we find is there's no areas with a lunar-like regolith. The big discovery here, the big issue here, is there's no powder. There are no areas like we saw on Itokawa or Eros where we see ponds of fine-grained material. That just does not exist on Ryugu. And so that provides a surprise. We were not expecting that. It provides a challenge, and that is what exploration is all about. This mission so far has been presented with many challenges, and the team here has risen to the occasion. We've had very successful landings, and now we are preparing for a successful touchdown and sample return. It's an engineering challenge, it's a science challenge. And we have here today Hikaru Yabuta, who is going to discuss with us those challenges and the decision process for selecting where we're going and how we're going to return a sample that's really going to unfold more of the mysteries that this object holds for us. So with that said, I'm going to pass the microphone on to Yabuta-san.
Hello, my name is Hikaru Yabuta from Hiroshima University. For the landing site selection, we focus on the region that meets both safety for landing and scientific values. So in the methodology of landing site selection, first, the landing site candidates were defined by engineering evaluation. In the first step, safety score analysis were carried out in terms of the surface roughness and orientation of spacecraft position evaluated by rotation model and shape model. And in the second step, a visual evaluation about the presence of borders were evaluated from the optical images acquired by ONC. And in the third step, a feasibility analysis were carried out based on the surface temperature and detailed distribution of borders. Then a scientific evaluation focused on science, that is physical properties, geology, and composition of asteroid surface. And safety, again, was evaluated by the scientific methods, and sampleability was evaluated based on the distribution of grain sizes and borders. So first, engineering evaluation selected the 7 possible landing site regions. That is L5, L7, L8, and L12 from the equatorial regions, and M1, M3, and M4 from the mid-latitude, from the safety score map. The safety score map is based on the sub-Earth distance and local solar angle and local slope and elevation maximum differences. And summer prediction results for the first touchdown was obtained by TIR. The temperature for each site were less than 350 Kelvin, which satisfied the safety condition for landing. Then candidate sites were narrowed down by counting borders. This figure shows distributions of borders larger than 3-meter diameter. The original images were acquired by ONC team. And as you can see, any regions looks like having equally many borders. And nevertheless, we try to find where the area occupied by borders are small, and we regarded L7, L8, and M4 as preferable sites for safe landing. Scientific evaluation, I would like to show one of the example. This is a map of spectral slope in the visible wavelengths acquired by ONC data and shape models. You can see slight extent of heterogeneity across regions. L regions are relatively bluish, and M regions are reddish. Considering that spectral leading is likely due to the secondary processes on the asteroid surface, such as space weathering, we prefer L regions showing bluer spectra that is probably reflected by the primitive materials. And in the total evaluation, science scores, safety scores, and sampleability scores were summed. And as a result, we selected the regions with highest scores, that is L8, L7, and M4. And the landing sites for MASCOT and Minerva were evaluated by individual instrument teams. And now I realize I put the instrument name oppositely. Sorry about that. Blue area is MASCOT and red area is for Minerva. And this month and last month, both lander and rovers successfully landed and made a great observation. In summary, the surface of asteroid Ryugu is composed of the mixture of materials with different origin and processes, and that will enable the sampling of material which represent the whole Ryugu. And a detail about border distribution and spectral map will be presented in the poster session this afternoon and the special session of Hayabusa2 tomorrow morning. Thank you.
I'd like to finish this presentation session by letting you know about the most recent update. So what I mean by most recent update is what is this? Is something wrong with the hard disk? But it's running. Okay, good. Ooh. So what I mean by most recent update is the operation done. No, it's wrong.
That's the wrong one.
Is this correct? No. Click this here. This one. Can I just click? I'll be sure. And so what I mean by most recent update is the operation done, 2 weeks ago and yesterday, actually. Those are the touchdown rehearsals. So before making this sampling operation, rehearsal, we have narrowed down the sampling landing site to this area. Originally, the landing ellipse was like 100 meters times 100 meters, but now it's a circle. It's a spot of the diameter of 20 meters. And this is the spot we have identified to be most safe. And what we have to do is that we have to improve the navigation accuracy so that we can make we can hit the hole-in-one to this spot. But is that possible? That's the question. So in the first rehearsal, what we did is to descend down to 22.3 meter altitude, and then the navigation accuracy was turned out to be 10.8 meters, which is okay. And then we also confirmed that one of the critical instruments, laser ranging finder, to be operating perfectly. So I think the hurdle is one of the hurdles is cleared at this point. Then the rehearsal that was just completed yesterday, we descended down to 12-meter altitude, and then we also confirmed that the target, we also deployed the target marker, which is like an artificial landmark, so that that enables us to make a very precise relative navigation on the surface. So which means that another tool that's necessary, that's very useful to make the more precise navigation is working. And we did not only deploy the target marker, but we have managed to capture it on the images. And we did the target marker tracking navigation as well, but the performance is yet to be confirmed. But in any case, this is another critical element, another critical hurdle that's been passed in the last rehearsal already. So we're really ramping up the steps towards a successful touchdown. That is to happen earliest in January next year. But from now on, in November and December, because the spacecraft is in the opposite side of the sun, we cannot do anything. But that leaves 2 months of time for the team to think about the details of the touchdown operations. They think they already have enough enough materials to deal with. The project manager told me that he had a beer party last night, so which is a good sign. And I think we'll make a successful touchdown, January earliest. Thank you very much.
Thanks to all the speakers. We'll take question and answers now. Before you ask your questions, please state your name and affiliation. Luca?
Luca Maltagliati, Nature Astronomy. First of all, I want to extend my congratulations to the mission, because images from the asteroid are great. So my question is, MASCOT landed on a rock, and the rock almost crumbled, or was reduced to small pieces. So does it mean, are these good news for the touchdown? I mean, does it mean that the rocks are less dangerous than they look?
Yeah, at least for MASCOT, it was not dangerous. So we just bounced back, and we calculating how much energy we put into the rock, but it was not dangerous for MASCOT. So we don't see any damage on MASCOT so far. We don't have any information on MASCOT, and we don't have any information on the damage of the rock.
The important thing is that.
Okay, but you have to be careful, because we have a very smooth velocity, so that MASCOT coming on the surface is something like this, so that in any case doesn't really expect damage of MASCOT itself.
Thank you.
Hanukkah Weidering with Space.com. My question, I think it's for Masaki, but anyone can answer it, I guess. So you said that you were shocked to see in the first images of Ryugu how rocky it was. But I'm wondering, what were you expecting it to look like, and how did you kind of form those expectations to begin with?
Yeah, it's not easy to review the stupidity that we have been in, but we had, we thought we have good experience with Itokawa, the target asteroid of the previous mission, Hayabusa the first, and there was some smooth terrain on the surface. So we thought that's the way it should be. There might be some rocky part, but there should be some smoother part, and that was the expectation. And why do we believe in it? I don't know. Maybe you can tell me. But we just thought that should be the state. That should be the surface condition of Ryugu. And yeah, maybe you can tell me why we have been so stupid.
Really, because all of the asteroids we have seen so far, Near or Steins or Matilda, all of them has some kind of accumulation of fine materials. They have regolith in a sense that there is also dust. And I think nobody expected that there is an asteroid which just shows rocks. So that doesn't mean that there is no dust. I think there is dust, but the dust does not accumulate in larger areas. And so, we need to look a little bit more into this in order to understand it, because dust normally forms a space weathering, so probably it's not weather at all.
I think it was from the thermal modeling, inertial modeling that other scientists were doing, and they calculated, I guess, the grain size of objects typically that size, and they were expecting like dust or regolith, but obviously it's not right.
These types of expectations are typically based on past experience and on what data that we can get from the ground that either collaborates that past experience or not. And, as has already been stated, in the past, we've always seen fine-grained regolith in patches that exist. But this is an example of why we explore. It never meets our expectations wherever we go, and that's the excitement, and that's the challenge. And so I think this team has shown, oh, we've got a challenge. They've buckled down and addressed it. So this is part of why we explore, to see the unexpected and to go ahead and forge ahead and do what we plan to do, return a sample.
Rick?
Okay, we have a number of questions online, and we'll see how many we can get to. This first one is from Alex Teleshev, who's a reporter for RIA Novosti in Russia. His question is about something we haven't raised yet this morning, which is the question of impacting the surface and observing the crater and the debris. He's wondering, how many opportunities do you have to do that? How many charges or impactors do you have? And, well, I guess that's it. That's the question.
We have one impact on board, so the chance is only once. And then the original plan was to do it in March, April next year. But we have been making changes in the plan. Original plan was to do the first touchdown at the end of October, which is around now. But because of this, because of the surprises, we have been changing the. We didn't delay it. I don't want to call it delay. We just rearranged the plan so that we would make the touchdown in early next year. So I cannot tell you about the schedule, but the team still has the plan to perform the impact experiment. So yeah, it's still there. Yeah, so, and the chance is only once.
Okay,
and then about the crater, the impact experiment is to make the crater and see what it looks like. But judging, maybe we can learn something already from the MASCOT experience, so that might be fed into the planning for the impact experiment as well.
Okay, then a question from Lisa Grossman at New Scientist. She's wondering, how does the thermal map tell you about grain size? Is it simply because bigger rocks retain heat more effectively?
All right, so I'm not the TIR expert on here. So it's based on the measurements and the modeling on how different grain sizes retain heat, how they emit heat. So that probably is a question that can be answered at tomorrow's oral session when Okada-san presents the TIR data in detail.
Hanukkah?
Hanukkah Weidering with Space.com again. Again, a question for anybody who cares to answer. When do you expect to release the new science results from any of the landers? And what can you tell us now about what might be coming up? What can we expect?
Okay, we have a wealth of data from MASCOT. So that means we have about 120 images we are working on. We have 17 hours observation of magnetic data and radiometric data. And we also have observations of spectral data. So, but usually it needs some time in order to get this data cleaned and in order to understand what we see. And what we already discussed is Ryugu is different from all what we have seen so far. So it needs a really evaluation of the data. The quickest one is look into the images, okay, because that's for itself, at least to give an impression. But we also have color images, so we have to look more deeply into this. That needs calibration. We have radiometric information, so that also gives grain size, that gives thermal inertia, but that also needs, in order to clean up the data, to understand the position to the sun of MASCOT, the position at each location, and also it needs to understand the distances. So we are not in the situation as the orbiter is. We don't know the distance direct. So we really have to first estimate and look whether we have enough stereo information in order to get distances. And this distances from our optics gives us the information of the size of particles on the surface. And that needs about, I think, 1 month or 2 months more. So I'm pretty sure that for the HEU we have much more information about details of our observations.
You have more online? Yeah.
Yes. Yes, here's another question from Alex Teleshev of RIA Novosti. Go ahead, sorry, I'll wait.
In terms of remote sensing observations, we are
Can you speak closer to the mic?
we are still working on calibration and analysis, but maybe this conference is very first conference to show results in academic oral and poster sessions. So please come to that.
Okay, so this question's from Alex Teleshev again, RIA Novosti, and I'm going to embellish it a little. He asks, are there any theories yet on how the asteroid got seeded with so many boulders? And my embellishment is, okay, so you've got all these boulders, you don't find any of the dust that you were expecting, and this thing is not shaped like a potato like most other asteroids, but appears to be shaped like an octahedron. What's going on? What do you know about this asteroid's history and evolution based on these unusual things that we're seeing?
Well, so we have our theories, and so now the next step is to test our theories. But from what we've seen, we can determine that Ryugu is more rubble pile. It's not a monolith that has been broken up. It may have been two pieces that came together. That's still something a hypothesis we're looking into. One of the things too is you have to, when you've got a conglomerate of pieces and you shake it, maybe what we're seeing are effects of the Brazil nut effect, where maybe the finer stuff is going down and what you're seeing is the excavation of larger boulders from beneath. So while these are our current hypotheses, these are the ideas we're going in and testing with the imaging data, with the thermal data, with the spectroscopic data. Once again, a plug for the posters this afternoon and the oral session tomorrow. You'll hear a lot more about the color observations and the spectral observations in terms of fresh versus young and how that relates with the variety of boulders we have, for example. So does that answer your question?
Well, I can't say for sure because Alex is online.
Okay.
But it does a good job, yeah.
Thank you.
We can take one more quick question, if you have any online.
Well, I have one question of my own,
Okay.
Which is, so what is the limit of the size of the particle that you can successfully grab? You apparently designed to retrieve a sample of regolith, of dirt, of dust. What if you get there and there really isn't very much of that? Are you going to pick up a bunch of stuff and it's going to fall because it's too big? What's the limitations that you're facing on what you can actually pick up and bring back?
So the way we do sample is that we touch the surface, and once we touch the surface, we shoot the bullet into the surface. So what we will be collecting is the debris created by this kind of a small-scale collisional experiment. So we will make a debris. We will make a small dust particles that's the way we designed the sampling operation. So even though there might not be small enough debris on the dust particle on the surface, we will create it by shooting the bullet into the surface. So we'll be touching down on the surface for 5 seconds. And during that 5 seconds, we shoot the bullet, and then we let the debris come into the sample container, and then fly back to the home position. That's the sequence of sampling operation.
About the size of sample, according to the design of sampler, the limit of size is about 5 millimeter. And in the point of view of sampling recovery, smaller grain size would be better. But in the point of view of intact composition of asteroid material, we prefer larger size. So, well, a few millimeter size would be the appropriate.
All right, and that concludes the press conference. This was the last one for this DPS, and hope to see some of you next year in Geneva. Thank you.